Right, it is April 13th. It's pretty late at night, so I'm going to try to make this quick. So the goal of this series is to explain the seed phrase algorithm and just recall our outline of the seed phrase algorithm. Um, the goal of the algorithm is to generate a tree of key pairs. So the first video I explained what a key pair was, and um, what I did, the way the key pair works is we have this elliptic curve. We have this group operation on the elliptic curve where we have 2 points and we can get a third point. And then we have this special limiting case. Let me find a better. Let me actually pick a point over here. That's a good. That'd be better. We have this special limiting case where the 2 points are the same point, and we can compute the so-called double of that point. So normally this operation to go from P and Q to the point R is called P plus Q, or point addition. And so, and it's called addition because there's a convention in math that if the operation is symmetrical, meaning I can swap the roles of P and Q and I get the same result. Um, so that's in math, anything that's symmetrical is called addition because it is. Um, anyway, we can compute the so-called double of a point by adding P to itself, and then, we'll get R. And then if we wanted to get, so R in this case, this would be P, R, you can't see where I'm pointing. We have P here. This would be 2 times P. Then to get 3 times P, we would take P plus R, which here we can actually, come on. We'd get like this point. Then to get 4 times P, we'd take P plus that point to get here. That'd be 5 times P. P plus this point would be here. That's 6 times P, and so on. And then your private key ends up being a randomly generated number, which is the n before n times P. So it's the number of jumps you take starting from a special point called the generator point. And your public key is the point that you end up at. Now, I also explained in the first video that computers are really, really bad at doing this continuous arithmetic because the arithmetic is inherently approximate. It's not exact. And in cryptography, everything needs to be exact. So, we kind of have a problem here. And what I explained kind of in a hand-wavy fashion was that we can actually do clock arithmetic. So, for instance, 6 plus 8 is 2 in clock arithmetic because, well, it's closer to 9 o'clock now. So 9 plus 6, it's like 9 o'clock right now. And in 6 hours, it'll be 3 o'clock. So 9 plus 6 is equal to 3 mod 12. And what I said was that if the modulus number, so the number of hours on the clock, if that number is a prime number, then it turns out that not only can we do addition in this modular arithmetic, we can also do division. And what division means in math is that you have, a number a, and you want to know what is 1 divided by a. Because if you want to do a divided by b, you just do a times 1 over b. But how do you compute a multiplicative inverse? That's what 1 over a number is called. How do you compute a multiplicative inverse in modular arithmetic? That's what we're going to talk about today. And so the point is that this picture that I'm showing you here, this motivated, somebody else, and somebody else converted this picture into some formulas. I copied those formulas off of Wikipedia. Those formulas to, go from P and Q to R, they involve doing division operations on like the points P and Q on the coordinate values of P and Q. And I think they also involve the curve parameters, if I'm not mistaken. They have to. Yeah, they must, because otherwise it would be different if you had 2 pairs. Yeah, it definitely involves. Yeah, because it's where does the point intersect the third curve? Yeah, for sure. What was I going to say? Okay, those formulas involve division, and what I said was that like kind of the whole thing with math, the reason it gets so abstract is because you sort of notice these patterns. You math. There's many definitions of math. There's a couple that I like. One is that math is the study of patterns. That's a good answer. Um, the second good answer is math is the art of precise analogy. That's, in a sense, the same answer. And then the third answer, which is also a really good answer, is math is the study of linear algebra. But all three of those are correct answers. I haven't heard another answer that I like. I like those three answers. But oftentimes in math, we kind of notice a pattern in one place and we sort of abstract out the pattern and we, come up with some sort of language to describe the pattern. And then we'll notice that there's the same pattern in a completely different object. So we notice this pattern in space, that space can be divided. And specifically, we notice that with division, that if you have, I don't know, the number 4, we notice this pattern that if you take 4 and you multiply it by 1/4, that this is equal to 1. And so therefore 4, or 1/4, is the multiplicative inverse. Of 4. And what matters, the definition of a multiplicative inverse of anything, the multiplicative inverse of n is some number m such that n times m is equal to 1. And then what is 1? Well, 1 might change depending on the context. And that's what I was saying about, well, we use plus for every operation that's symmetrical because, like, we notice that pretty much everything symmetrical behaves like addition. And so we might as well just use the addition notation because we're lazy and we like, doing operator overloading to show people how clever we are. So in the context of modular arithmetic, so I want to, fully flesh out all the math that's going on here. Not fully, because I'm not an expert in algebraic geometry, but, partially, as much as I can, to the maximum extent that's feasible, kind of flesh out the math that's going on here. And in order to explain that, I do really need to explain what modular division is and how it works, because it's not that complicated. Okay, so I gave you an example, which is that in Mod 7 arithmetic, let me just put parentheses around these because, infix operators, that in Mod 7 arithmetic, 4 times 2 is equal to 8, but Mod 7, that's 1. And if I have maybe a really, really big modulus here that's prime, and while I'm explaining how to do this, it'll be obvious why prime numbers are important. So hold that question. But how do I find, if I have, I'm trying to think of a really big prime number. I have an example here. I don't know where I put the example. I don't know, but imagine that, this was a much bigger number that was prime. And we wanted to find the multiplicative inverse of 4 mod that really, really, really big number. Maybe it's the number we use in elliptic curve cryptography for our elliptic curve. That's a number that's, hundreds of digits long. Okay, well, the whole point of having such a big array of numbers is that it's infeasible computationally to enumerate through all of those and figure out, which one is which. We can't just check every single one. There's too many. And so we need some very systematic, very fast way to just get to the answer. And that's what I'm going to show you today. And this will also kind of, in doing this, give you some idea of how numbers work, which is important. You can never spend too much time on fundamentals. All right. So what's our sort of game plan here? So let me game plan. Okay. So what actually turns out to be important, actually almost more important than prime numbers, is the greatest common divisor between two numbers. So we're going to talk about how to compute GCDs. And let me just get into that pretty much straight away. Okay. Because I can illustrate that really quickly. Let me just find it. Here it is, visual intuition for the Euclidean algorithm. So Euclid was a mathematician from 300 BC. He lived in Alexandria, which is near Cairo. Let me zoom out. Okay, and you should look at this picture. The algorithm is really simple. And back then, Euclid's sort of the father of mathematics. Mathematics, the sort of obviously there was mathematics before Euclid, but Euclid was this mathematician who took basically everything that was known in the sort of Greek canon of mathematical knowledge at the time, and he systematized it. So, and I think this algorithm was original to him, which was, given two numbers, how do you find the greatest common divisor between them? And everything was geometrical back then. And I think that's really a better way to learn math. It's not a better way to do math, but it's a better way to learn math. And the way that he phrased it, or the way that I think the way he phrased it, so what I'm going to say is that we have two segments here. We have this segment that's 210 long, this segment that's 45 long, and we want to find the biggest segment that evenly divides both of them. Does that make sense? So I have 210 and 45, and I want to find the biggest segment that evenly divides both of these segments. And I think the way Euclid phrased it was that he made a rectangle, so that was 210 by 45, and he wanted to find a square that tiles the rectangle, which is the same problem. And you can think about why. So the way that this works is we take the smaller number and we keep duplicating it until the point at which, if we duplicated it again, we would overflow. Okay, and then the remaining length is called the remainder. The number of times we duplicate it or replicate it is called the quotient, and the length of the remaining segment is the remainder. I just told you this. The most important observation to make here is that any number or any segment that evenly divides both the original two segments is also going to have to evenly divide the remainder, because it's going to divide this pink segment, this pink segment, this pink segment, this pink segment. It's also, going to divide we're going to get, an equivalent partition up on the big green segment here. And therefore, this remaining segment is also going to be evenly partitioned, because we assumed that a precondition of me talking about this was that we have some, segment that evenly divides the green segment and the purple segment. So it's got to divide this little blue remainder segment. And so therefore we can break the problem down into a smaller problem. So, and just generally, that's always good. So 210 is 4 times 45 plus 30. So this reduces into finding the GCD of 45 and 30, and you should be able to do that in your head. It's 15. But systematically, 45 is 1 times 30 plus 15. 30 is 2 times 15 plus 0. And we stop when we get a 0 remainder. And then this number here is the GCD. And so I think now is just a good opportunity to go over to the code and look at how this works, because I think I can just explain everything else, and I'll link to a paste bin of this code down below. So, it turns out, and I did a lot of experiments to check this, and at some point algebraically I worked out why this makes sense, and I don't remember. Exercise for the viewer. Here we assumed that both of these segment lengths are positive and that we put the bigger one first. Turns out you don't need to do that. And here signedness really doesn't matter. It would just impose a direction. It will matter in a second. Okay, but the GCD, what is the GCD of a segment with 0? This doesn't make any sense geometrically, but mathematically, okay, you remember how we talked about how we use plus for something that's just not addition when we were talking about, the group operation on points? The term in general for that sort of thing in computing, it's called overloading, but the more general term I would call implicit context swaps. And mathematicians love doing implicit context swaps because it makes you feel so clever, and it makes it impossible for anyone else to understand. So there's an implicit context swap going on here, which is the meaning of the word greatest. Now, you, being a pleb who doesn't know anything about math, might think that the word greatest means the biggest number, but you're stupid, and that's why you're watching this video and I'm teaching. Because the word greatest actually means, whenever you say a word like biggest or smallest or best or whatever, there's implicitly some sort of ordering operation that you're referring to. And the ordering operation we're referring to actually is the divisibility graph on integers. So just as an example, we have 210 here, and we'll just point to the bigger number. And 45 and 30 both divide 210, and 15 evenly divides both 45 and 30. So greatest means the biggest number with respect. Here, let me put the nodes in a different color. Okay, and then there's another one down here, which is the bottom node. And this is 1. Because 1 divides every integer, and every integer divides 0. Because there is always, what does it mean for A to divide B? This is the standard notation. It means I'm going to just gradually introduce you to math kanji. There exists some number q, which has the property that q times A is equal to B. Okay, well, every number divides 0 because 0 times that number is equal to 0. Okay, so 0 is the biggest number with respect to the divisibility graph. So what we're actually looking for is we're looking for the biggest number on this divisibility graph, biggest with respect to the divisibility hierarchy, that divides both 210 and 45. Okay, So that's why the greatest common divisor of anything with 0 is anything. Okay, and also negative and positive make this just more complicated in a way that's really stupid, because then we have actually another parallel divisibility graph with, minus 210, 30, 45, and of course 15 divides both minus 45 and 45. It's stupid. We can get exactly the same logic by just talking about non-negative integers. So I'm ignoring that. You're welcome to make it complicated if you want. I'm not going to. That's not why I'm doing this. Anyway, algebraically, that expression. So remember, we had a. So the bigger number is something times the smaller number plus a remainder. Well, it was obvious visually that anything that divided this, the big segment and the small segment. Let me pull up the graph. Where is it? Come on. There we are. Okay. It's obvious geometrically. Where is it? That anything that divides, the big number and the big segment and the small segment also divides the remainder. It's also obvious algebraically, because we can rewrite this as a minus q times b is equal to r. And therefore, any number that evenly divides a and b, any number that divides a and b will also divide a minus q times b, because that's how fractions work. And therefore, because it divides this and a minus q times b is equal to r, it must also divide r. So it's algebraically obvious too. But I want to, if there's given a choice between explaining something with geometry, with a picture, and explaining something with algebra, I'm always going to prefer the picture. And you should too. So, so it's obvious here that, so it's obvious visually that this just works, but algebraically it's not obvious that this just works. So one way you can be convinced, it's obvious that this will converge to a common divisor of a and b, because there's nothing here that breaks divisibility. Everything dividing a and b is preserved at every step in this process. But but why does it converge to the greatest common divisor? Well, you can make sort of a bounding argument here. So, anything that divides a and b also divides r. So therefore, the greatest common divisor of a and b, being a common divisor of a and b, also divides r. By symmetrical logic, because, we have qb plus r is equal to a, so anything that divides b and r also divides a, we can say the GCD of b and r must divide a. So we can make a bounding argument. And remember, this is a bounding argument on the divisibility graph. The GCD of b and r, it divides a and b. Therefore, it's less than, with respect to the divisibility graph, it divides the biggest number that divides both a and b. So, so the GCD of b and r has to divide the GCD, or is less than or equal to. It's the biggest number that divides a and b. But the logic is symmetrical, so we can also say that the GCD of a and b also divides GCD of b and r by exactly the same argument, because, well, this divides b and r, and so does this, so therefore, this divides this. And, if a divides b and b divides a, then a is equal to b. Okay, so all we're doing here, so in Erlang's a really simple language. So this is saying if the second argument is 0, the way we do if-then statements, if you're a programmer, the way we do if-then statements in Erlang is, instead of if-then, which there is in the language, but you're not supposed to, you can use it, but you shouldn't. Instead, we do our branching in the sort of function heads here. So this is saying if b is equal to 0, then we take the absolute value of a, because again, just for my own sanity, I always want the GCD to be positive, though there's no mathematical reason why it should be. So GCD of anything with 0 is the thing. If we have two numbers, A and B, the GCD of B with a remainder B, so the remainder when you take A divided by B, that's this segment over here. That's what A rem B is. And so all this is saying is the GCD of 210 and 45, compute this little segment here, take the GCD of that of pink with blue, and that's the answer. And that's it. Okay. So how on earth does this allow us to compute modular division? Okay, well, that's the next step in this process. So now we know how to compute GCDs. It's really straightforward. The next thing is a really interesting fact, which maybe is plausible geometrically, and I wasn't able to think of like a good visual way to explain this. But if, let's suppose, we have A and B, and and their GCD. It turns out that it's always possible to find coefficients, which I'll call Q, QA times A plus QB times B, which is equal to the GCD. Now, geometrically, what this would mean is that between 210 and 45, there's some number of jumps we can take in one direction with 210 and then jump back a different number of times in the other direction with 45, such that the total distance we would end up traveling, the net distance or the net displacement, whatever, would be this GCD, would be this segment that evenly divides both of them. It turns out that everything that they do, so it's possible to find QA and QB such that QA times A plus QB times B is equal to the GCD. And I'm going to show you how to do that in a second. Now, the way that this gives you modular division is that, well, suppose, we have, n, and we want to find 1 over n mod p, where p is a prime. Well, the GCD is going to be 1. Right? We're going to be able to find Q sub n times n plus Q sub p times p, which is equal to 1, because that's going to be their GCD, because that's what a prime number is. Another way of phrasing this is Q sub n times n is equal to 1 plus, it'd be minus Q sub p times p, but what this is saying is that Q sub n times n is equal to 1 plus some multiple of p. So another way of phrasing that, Q sub n times n is 1 off from a multiple of p, i.e. Q sub n is equal to 1 over n mod p. Does that make sense? And, definitely watch it again if it doesn't. But I don't know a way to explain that more straightforwardly. So how do we compute these coefficients? It's similarly fairly straightforward. It's just a matter of making a clever observation and then doing the obvious thing. So given A and B, return a triple. This is a tuple. If you're familiar with like Python or something, this is what tuples look like in Erlang. God fucking damn it, Katie. Did Leonard come to pay us a visit? Leonard better not have come to pay us a visit. Okay, Leonard seems to have backed up. Leonard is my nemesis. All right, so again, we're always returning. So what we want to do is return a triple QA, QB, Q, and GCD that has the property QA times A plus QB times B is equal to the GCD. So convention, remember, GCD of anything with 0 is the thing, but we're always returning a positive GCD. So if we're given a negative number, we return minus 1 times A plus 0 times B is going to be minus 1 times A, which is the GCD, right? Write that down on a piece of paper if you don't believe me. The this is called the extended GCD algorithm. That's why it's an E. The EGCD of A with 0 is 1, 0, and A. So 1 times A, this is the GCD. This last one is the GCD. 1 times A plus 0 times B. It literally doesn't matter what we put here, but anything works. 1 times A plus 0 times B is equal to A. Okay, this next one's a little bit confusing. Once again, we're going to break this down into a smaller problem, and it just comes from doing some algebra. And maybe I'll write this out here, but I think this is fine. So what we'll do is we'll find, and I'm put underscores here to emphasize that this is kind of a different thing. So we have QB under times B plus QR under times R is equal to the GCD. So we find that by just doing the same trick, calling EGCD on B with the remainder. Okay? So again, maybe going back to the picture, we want to find coefficient, some jump on A, some jump on the big number and the little number that gets us to the GCD. Well, what we'll do is we'll find a number of jumps that work on the little number and the remainder that get us to the GCD, and then from there figure out use some algebra tricks to get things that work for the bigger number. So once again, QB times B plus QR times R is the GCD. Well, remember R is A minus Q times B. So we're just going to do a direct substitution from this equation. We're going to make this substitution. That's all that's going on here, as I replaced R with A minus Q times B. Otherwise, this equation and this equation are identical. So QB times B plus QR times A minus QB is equal to the GCD. Okay, well, we regroup the terms doing algebra, and pause the video and do this if you can't just visualize it. We get QR times A plus QB minus QR times Q times B is equal to the GCD. So this is going to be our QA, is QR, and this is going to be our QB. And that's going to get us to the GCD. Okay? This is just algebra. So once again, we want to find coefficients QA times A plus QA times So here's the thing in Erlang is that let me back up. We want to find QA times A plus QB times B. We want to find these numbers QA and QB. That's what we're returning, and the GCD, such that the GCD is QA times A plus QB times B. The way we're doing this is by, breaking it down into B with the remainder, then doing some algebra to figure out what QA and QB are in terms of the results from doing this on the remainder. That's it. So now here's a thing in Erlang. So here, most languages, if I say x is equal to 5, x is 5. And then if I, on the next line, say x is equal to 4, well, x is 4 now. Erlang doesn't work that way. If I say x is equal to 5, and I say, what is x? Then on the next line, I say x is equal to 4. In the shell, it just prints out a message, but in a real program, it crashes the program. So assertion or assignment in Erlang is also assertion. So this crashes the program if this statement is false. Okay. So this should just make sense. So the point is that we can find these numbers, and how we actually find these is not really that important. What matters is now we want to do modular division of A divided by B mod P. Well, we just take the product of A with 1 over B, mod inverse, mod P. Okay, how does mod inverse work? It turns out P does not have to be prime. It just has to be relatively prime with B, which means its GCD with B is 1. So a prime number is a number that's relatively prime with every smaller number. That's, yeah. So relatively prime means just its GCD with the number is B. So the GCD of B and P has to be 1. And you'll notice the logic before. The reason we wanted prime numbers is so that every number had a multiplicative inverse, but it only, if we're just computing a specific multiplicative inverse, all that matters is that that number, that the bottom of the fraction is relatively prime with the modulus. So there you go. That should tell you why prime numbers are important. I mean, prime numbers are important for so many reasons, but that's one of them. Okay, so 1 over b mod p. So once again, we compute qb, qp, and 1. This is going to be the... So this is, again, asserting that the GCD is 1. This will crash if you give this... if we tried to compute 1 over 9 mod 12, this would crash because there's the GCD of 9 and 12 is 3, right? Yeah, it's 3. And interesting fact, which will become important later, but isn't important right now, it's possible to do, some jumps with green and then jumps in the opposite direction with purple to get the GCD. It's not possible to get any segment that's smaller than the GCD. This is the smallest you can get. And likewise, any jumps that you can make with, so any combination of 210 and 45 is going to be some multiple of the GCD. That's a succinct way of phrasing it. So it's not possible to get anything smaller than the GCD, and anything that you get that's bigger is also some multiple of the GCD. And geometrically, that should at least be plausible. I don't know a good way to illustrate it, but that should at least be visually you can maybe kind of visualize how that might be true. I don't know a good way to cleanly explain it, but algebraically it's not difficult to explain. I don't remember how to do it off the top of my head. All right. And the rest of these are just, so let me just show you. If I do -3 rem 4, it'll give me -3. And what I want, because I'm me, this is completely inconsequential mathematically. Let me, okay. Okay. Oh, oops. All that this mod function does is just give the positive version of it. So 1 is equal to -3 mod 4. It's exactly the same in modular arithmetic. They behave exactly the same way. But okay, so that's how we do modular division. It's super thrilling. But again, qb times b plus qp times p is equal to 1. So qb times b is 1 plus some multiple of p. And there we go. That's it. It's mod qb of p. And this is a sanity check. It's just checking 1 is qb times b mod p. And let's just test this for a second. Mod inverse of 4 mod 7, this should give us 2. And, 2 mod 7, it'll give us 4. Okay, what's 1 inverse mod 7? Well, what's something you can multiply 1 by to get 1 mod 7? It's 1. 6. Well, 6 times 6 is 36, which is 35 plus 1. So the answer is 6. And so 5 and 3 should also be inverses of each other because those are the only numbers that are left. And there we are. That's it. That's the whole thing. That's how to do modular division. It's kind of technical, but it's super straightforward. I'll put a link to this article and a paste bin of the code so that you can play with it down below. Holy shit, 40 minutes. All right. Bye.